Hola, yo soy Adrianna. I'm so excited to be here with you all today. It's my first time in Brazil, and I can't wait to meet more of the Rails community here. It's been a great day one so far. Oh, I went too far. My name's Adrianna. I'm a staff engineer at Shopify. I work on our Rails infrastructure team. I'm also a member of the Rails issues team, and I've been working with Ruby and with Rails for about a decade now. So a little bit more about me. I traveled here from Ottawa, which is the capital of Canada. One of the most famous things in Ottawa is the Rideau Canal, which is a canal that freezes over in the winter, and it's actually the world's largest skating rink. I live with my husband and my rescue dog. This is Jasper. He's my baby. And I love to do things outside. I love to run. Recently, I've gotten really into triathlon, which is where you swim, bike, and then run. So I have a lot of fun doing that. And I work for a company called Shopify. We all just watched a video about Shopify. Some of you may be familiar with us. We're an e-commerce company. We power commerce all around the globe. We have over 1 million merchants on our platform, everything ranging from small first-time sellers to really big enterprise brands. And most excitingly, Shopify is a Rails app. We're built on Rails. We have one of the largest and highest traffic Ruby on Rails applications in the world. Our core monolith has millions of lines of Ruby. We have tens of thousands of tests and thousands of engineers who work on it every single day. Everything from checkouts to shipping and fulfillment to inventory all goes through Rails. So Black Friday, Cyber Monday is a really big weekend in commerce. It's our biggest weekend of the year at Shopify. Last year, Shopify scaled up our Rails app to handle 14.8 trillion database queries over the course of the weekend. At peak, we were serving 489 million requests per minute and processing 11 terabytes of logs per minute. And all of this through Rails. At Shopify, we don't use Rails despite our scale. We've really grown with the framework. When Rails succeeds, Shopify succeeds. When Shopify learns how to do something hard, we try to bring it back to the framework so that the Rails community can benefit too. We care deeply about open source and about investing in Rails for the long term. So one of the ways that Shopify invests in the open source community is by paying a team of engineers to work on Ruby and Rails full time. I'm really lucky I get to be a part of this team. This is some of us at Rails World last year. Raphael, who is one of the co-organizers of this conference, actually started this team about a decade ago, and it's now grown to about 40 engineers, so we've got a great team there. We get to work on a lot of cool stuff in Rails, things like composite primary key support, development boot time improvements. We worked on support for the Trilogy active record adapter, and a lot more. Something else we worked on was adding structured logging to Rails, which shipped in Rails 8.1. I talked about some of this work on the event reporter at Rails World last year, and today I want to tell you more of the story behind structured events. You see, we built the structured event reporter because Shopify needed a better solution for logs. But from the start, we knew we wanted to build something useful for the Rails community. This was a little bit of a balancing act, meeting Shopify's needs while creating a feature that could be upstreamed. In today's talk, we'll look at the process of developing a large feature like this for Rails, and I'll share some of the things that I learned about contributing to open source. So on the agenda for today, we're going to start by talking about how Shopify handled observability before the event reporter and why we needed something better. We'll talk about changing our thinking from seeing logs as just logs to viewing them more as events. We're going to get into kind of the details with the event reporter. We'll talk about the design choices we made, how we managed to build something for both Shopify and for open source. And finally, we'll talk about contributing some of that work back to Rails and why open source contributions matter for everyone. So let's get started with the need for better tooling. Our story starts in August of 2024. Our team, Rails Infra, found out that Shopify was planning this really big change. We were going to replace Splunk, which is the logging tool we'd been using for years, with a new internal platform called Observe. There were a bunch of reasons we wanted to move to Observe. The big one was money. Splunk was costing us a lot of money. And we wanted to be able to scale up our infrastructure to handle a bigger volume of logs. So not only were we switching from Splunk to Observe, but we were actually going to build a new logging library to replace the Rails logger. Like most apps, we were using rails.logger for all of our logs. Splunk is really good at text-based search, so the standard Rails logger and unstructured logs had always been good enough for us. But Observe wasn't going to be able to index freeform text like Splunk did, so unstructured logs were no longer going to cut it. We needed to structure our data, and Shopify decided it was time to build a new API to support this. Now, this tends to be a common problem with rails.logger. It works really well when you're developing locally and reading your logs in the console, but the logs it produces don't scale well in production. Most observability platforms, modern observability platforms, can't do very much with plain text logs. Even with a tool like Splunk that's good at querying text, it's hard to search the logs unless you know exactly what it is you're looking for. Rails.logger is also not very opinionated. Anything you want to log, you can log. This is a real example from our code base. We had this cart drop class that held an attributes hash. The details here aren't super important, except that we were overriding hash to basically log every key access into the hash, like that, which, as you can imagine, produced a ton of logs. They weren't super meaningful. It was creating a lot of noise. So our CEO, Toby, who you just saw a much younger version of Toby in that video, he had a clear ask. We need an API that is more opinionated and that helps developers do the right thing. So a new API was going to be built inside Shopify, but we knew that the Rails community also wanted something like this. At the time, there was an open issue from DHH describing the need for structured logging in Rails. He pointed out the main problem with the Rails logger, and that is that unstructured logs are easy for developers to read, but hard for machines and analytics platforms to use. You may also notice in this issue that DHH mentions that both Shopify and 37 Signals have been using in-house structured logging for a long time. Well, what do you mean Shopify was already using in-house structured logging? As it turned out, Shopify had actually built an internal gem for structured logging years earlier. It was called the canonical logger. Most of our Rails apps used it by default, but our main monolith didn't. It had always had its kind of own custom logging setup. The canonical logger added a new method to the Rails logger called log_append, which let you attach structured data to a request log. And then at the end of the job or the request, we would take all of that data, we would combine it and write it as basically a single JSON line. We would capture some extra data by default, things like the request ID, performance stats, and more. And all of this would get kind of emitted at the end of the job or request. So here we were, about to build yet another structured logging API inside the monolith. You might be thinking, why not just try to use the canonical logger in your monolith and try to contribute that to Rails? Well, the canonical logger had its own problems. First of all, it was very rigid. If you wanted to change the information that was captured in the request log by default, you had to kind of go into the library and change low-level code to customize anything, and it was super coupled to Shopify's infrastructure at the time. The second problem is that the canonical logger actually replaced the standard Rails logger. Any regular logs, so if you called rails.logger.info or rails.logger.debug, those logs would just be dropped, which meant logs that Rails normally emits as part of the framework weren't captured in production with the canonical logger. It also meant that the developer-focused logging experience was gone. Developers had to read through these giant JSON payloads in development to understand what was happening. And finally, the canonical logger couldn't produce individual log lines. It was designed to produce these kind of aggregate request or job summary logs. We would combine everything from the request into a single payload. The observability team at Shopify really wanted to switch to individual logs, where each call to the logger created a separate log that could be queried by name. And the canonical logger wasn't built to support this. So this library wasn't a good fit for contributing to Rails, and really, logs were only a small part of the picture. We were creating events in many different ways throughout our code base. For example, we were sending logs to Splunk, but we were also tracking business events in an internal system called Monorail, which we'll talk about a little bit more later. We were also writing audit events to the database just through Active Record, and we were sending metrics to statsd. So it became clear that we needed kind of more than just a solution for structured logging. We wanted a simple, consistent API for creating any kind of event in a Rails app. So we needed to shift our thinking from thinking about logs to thinking more holistically about events. So what exactly is an event? An event is a named record of something important that happened in your application. It includes context, like what happened, to which object, when it happened, and often where in the system and why. Events are semantic, meaning that they are easy to parse and extract useful information from. We can think about this in two ways: keys and schemas. Key-level semantics means that fields have consistent meaning. For example, a consumer can reliably extract shop ID from a shop plan changed event like this because everyone agrees on what that field means. But with key-level semantics, all we really know is that there's a field called shop ID in the payload. We can guess that it probably refers to a shop, but we're still making an assumption here. There are frameworks like OpenTelemetry that help by setting naming conventions for fields, but there's still a level of guesswork here. So this is why schema-level semantics matter. Here is a schema definition for that same shop plan changed event. This is protobuf. If you're not familiar with the syntax, don't worry. The details aren't super important, and we'll talk a little bit more about protobuf later on. But the important thing to note here is that with a schema, we don't have to guess what shop ID means. The field's type, whether it's required or optional, and its purpose are all defined in one document. Schemas give consumers a complete picture of what an event looks like and how it has changed over time. Ultimately, schemas are contracts. Developers can read a schema file and know exactly what fields exist and what they mean. Schemas are also useful for machines. They make it possible to generate code automatically, validate data, use LLMs to help with migrations, and to join data across different event sources. Later, we'll see how Shopify used the event reporter to power schema-based events in our code base. One last thing about events. Logs actually are events, but events are, conversely, not always logs. Logs typically refer to developer or operational events. As software developers, these are usually the types of events that we're used to working with. But event is a much broader term. It also includes signals like metrics, traces, spans, and business events. The difference is really only where these events are sent and who consumes them. So the event reporter wasn't designed only for logs and structured logs. It's really meant to be a general purpose interface for creating any kind of structured event in your Rails application. Okay, so jumping forward to September of 2024, it's a couple of weeks after we learned about this big move from Splunk to Observe. Our team decided to take the opportunity to build something for Rails, but we needed to find that balance of meeting what Shopify needed and building something that made sense for Rails. For Shopify, we needed a structured logging API that supported individual named log entries. This API had to work with Shopify's observability tooling. Notably, it had to be able to send data to Observe. We also wanted to use it for business events, which meant supporting events with schemas. And finally, we needed an easy way to collect context throughout a request and attach that context to every log. What about on the Rails side? Well, the API had to be generic enough to work with any Rails app, no matter what observability stack it used. Most apps probably wouldn't use schemas, so it had to support simple hash-based payloads. Rails would need to define a standard shape for events and capture certain defaults, like the timestamp and source location. And finally, it had to work well with existing tooling in the Rails framework. It needed to work with the Rails logger, and it needed to work with Rails framework logs. So let's look at a few parts of the event reporter and finding that balance between building for Shopify while keeping an open source lens. We'll start by talking about how we kind of landed on the event reporter as an interface. Next, we'll look at how Rails actually builds events internally and how those events get sent to subscribers. We're going to talk about supporting events with schemas and how we replaced our internal system monorail with structured events. And then finally, we'll look at how we designed a way to track context throughout a request. So how did we come up with the event reporter as an interface? We started by looking at what the observability team had built to understand what Shopify needed out of a logging library. Observe.log was the API that they'd created for producing structured logs. You called it with a name and a structured payload. And then in the back end, we'd validate the fields, we'd merge in some extra context from the request, we would then serialize that message to JSON, and we would send it to Kafka. Eventually, the log would flow through the logging pipeline, and it would kind of magically end up in Observe. So Shopify already had clear opinions about how developers should write logs. Logs needed a clear name. They could also include a human-readable message. This was optional, but helped kind of bridge the gap between working with unstructured logs, which developers were really used to working with, and working with kind of data in a structured format. And then finally, most importantly, logs needed to contain real structured data as a hash of attributes. So one of the first APIs that we tried to mirror observe.log was adding an event method to the Rails logger. We knew that the default Rails logger was a broadcast logger, which meant it could write messages to multiple outputs. So we thought, well, maybe we can just kind of extend the Rails logger so that it can send structured messages to consumers who want to consume structured data. So the idea was to have an event logger class that could receive structured messages through an API called event. So you could do something like rails.logger.event, pass in a name, pass in some structured data. The event logger would build an event hash, and it would send it to a sink. You can think of a sink as a consumer that basically collects and processes structured data. So the event logger could be configured with a sink directly or with a log device, like how a typical logger is configured. In production, we would typically want to hook this up with a sink directly. For example, we might have something like a Kafka event sink. So the event logger builds the event, it sends it off to the Kafka event sink, and then the Kafka event sink is responsible for formatting the event into a message for Kafka and exporting it to a Kafka pipeline. But in development, we could create the event logger with a log device, maybe standard out. And when we use a log device instead of a sink, the event logger basically wraps the log device into a log device sink, like that. So the log device sink is responsible for taking the structured data that it gets from the event logger and turning it into an unstructured log line that can be written to an I/O. So for a simple example, in this case, we have a log device sink. It receives a structured event for something happened from the event logger, and then it's going to take that event and basically just turn it into something that can be written to standard out. So with the event logger approach, the thinking was that apps could register their own sinks to validate, encode, and export data to any consumer. So we could have an event logger for Observe, we could have one for Monorail, we could have another one for StatsD, basically as many event loggers as you want. So this API made sense to us at first, but the more thought we gave it, the more we realized that something wasn't quite right. Because the Rails logger is a broadcast logger, calling rails.logger.event would send the message to every registered logger, including plain active support logger instances with no idea what event is. So to make this work, we would need to add an event method to active support logger to convert structured events into basically plain text logs. And the reverse was also true. Standard logger methods would be sent to event loggers, so they'd need to know how to turn plain text into structured data. Keeping things compatible in this way was going to add a lot of complexity. And really what we realized is that loggers are designed to work with log devices like files, sockets, and standard out. They aren't really meant to work with consumers that expect structured data. Loggers also revolve around log levels. We were adding an event method to the Rails logger almost as if it were a new log level, but log levels are really meant for controlling volume. So this didn't feel quite right. This is when it really clicked that while logs are events, events are not logs. Adding this to the Rails logger felt like the wrong abstraction. We needed a new API. So one thing that came to mind right away was the error reporter. Some of you may be familiar with the error reporter. It's a common interface for sending errors to error reporting services. So we thought, why not build something similar, but just for events? So this is what led us to the event reporter as an interface. It's an interface for sending structured events to subscribers. We chose rails.event.notify as the API to replace observe.log. So you pass in an event name, you pass in a set of structured data, and Rails will handle the rest. So this is the first lesson of building for open source. Finding the right API is often the hardest part, and it's important to be patient. Adding a new feature to Rails might not be technically super hard, but figuring out where it belongs in the framework and how to make it feel like Rails isn't always easy. In our case, adding event to the Rails logger felt complicated and unintuitive in the end. When we found the event reporter as an interface, we knew it was the right fit. Okay, so we had an idea of what we wanted the developer-facing API to look like with rails.event.notify, but how would notify work under the hood? We needed it to build consistent event payloads and send them off to any number of syncs, including observe. So let's take a look at how notify works. You'll notice that it takes a name and an event name and a payload hash. So you can call rails.event.notify. You can provide a name and a set of structured data. We also support just passing in data as keyword arguments. In some cases, it's nice not to have to build that extra hash. You can just pass everything through. And Rails provides a consistent shape for events. You'll see here that we build an event hash with a fixed set of keys. Remember, we talked about kind of the 4 W's with events. Events include what happened, when, where, and why. So the event name tells us what happened. The timestamp tells us when. The why is captured in the structured payload. It's also captured through things like tags and context. We'll talk a little bit more about that later. And the where is the event source location, which we capture from the call stack by looking at caller locations. The event reporter by default provides this as the file path, the line number, and the label for the event. So this is the final shape of an event from the event reporter. Developers can focus on including their own domain-specific context in the payload, and then Rails fills in some extra defaults and gives us an event with a predictable shape like this. Let's look at how you connect consumers to the event reporter. So apps register subscribers using the subscribe interface like this. Subscribers must implement emit, which the event reporter calls with the event hash. We chose the term emit because subscribers typically emit events to a downstream sync or consumer. So internally, the event reporter stores a list of subscribers. If we want a subscriber to only listen to certain types of events, we can register it with a filter. That looks something like this. Basically, you specify a proc, it receives the event, and it can basically evaluate whether that subscriber should receive the event or not based on whether the proc returns true or false. In Notify, we filter the list of subscribers to only the ones that care about the event, and we do so by calling that filter that was registered. And then if no subscribers care about the event, we return early. Then, once we've built the event hash, we iterate through each subscriber, and we call emit with the event on each one. If a subscriber raises an exception, we use actually the Rails error reporter to handle it. Using a subscriber approach like this meant that we could connect an observed subscriber without adding anything Shopify specific into the API itself. Here is a super rough outline of what our actual observed subscriber is doing in the code base. We won't go too deep into the details, but just at a high level, we do some sampling. This just makes sure we avoid processing a ton of events in really high traffic code paths. We do some validation to try to catch bad payloads. We do some type checking here. We assemble the log record based on the events data from the Rails event, and we add in some available context. We encode the message into a message pack batch. So we batch up messages, and then we export them in a batch. And we have some instrumentation around the subscriber itself. This is to make sure that logging in our application remains really fast because we're producing a lot of logs in our code base. So you'll notice that this is actually super similar to what we talked about observe.log doing before. And actually, we were able to reuse most of the existing logic when building out the subscriber. We really just needed to plug it into the event reporter interface. So lesson number 2, convention over configuration, but configuration when necessary. Rails sets conventions for what structured events look like and how they should be created, while letting apps configure their own subscribers. Rails is opinionated about the API for creating events, but gives apps flexibility over how those events are encoded and sent to consumers. Okay, next we're going to talk about schemas. So remember earlier we talked about wanting to build something that could unify these different types of events in our code base. One of the key use cases we had in mind was Monorail, which is Shopify's internal system for creating and processing business events. With Monorail, apps would define schemas for their events in YAML files that look something like this. So this is a schema for shop plan changed, which represents a shop's subscription plan changing. Apps could call monorail.produce to create a structured event based on the schema, and this would produce a structured JSON message that looks something like this. It has the name of the schema, it has the payload, all encoded as JSON. Remember, schemas are contracts. For business events like this, having an explicit schema is critical for making sense of the data. But actually, internally, Shopify's engineering leadership wanted to stop using Monorail for business events and switch to something called protobuf. Protobuf is a language-neutral data serialization format developed by Google. The goal was to use it for both defining schemas, so as a schema definition language, and as a serialization format. So we define schemas in proto files, and we would serialize those events to proto-binary for transport over the wire. So here is that same shop plan changed event written as a proto-schema. Protobuf supports reading and writing structured data in many languages, including Ruby, and it also includes code generation. So protobuf allows us to compile a proto definition like this into a Ruby object that basically works just like any other Ruby class. So the desire to move from Monorail to protobuf lined up actually really well with our work on the event reporter. If rails.event.notify was able to accept proto objects, we could pretty easily replace a call to monorail.produce like this with a call to rails.event.notify, passing in that proto-generated object. So this is why we wanted the event reporter to support objects with schemas. Let's take a look at how Notify supports this. So as we saw earlier, Notify can take a name, but it can also take an object directly. This object should represent an event. When we call resolve name here, we generate the event name using the object's class if an object was passed. And when we resolve the payload for the event, we actually just pass the whole event object through. The event object gets preserved and passed into the payload so that subscribers can access it. We'll see why in a second. So in the end, the event reporter produces an event hash that looks something like this. The event name as I mentioned, comes from the Ruby proto object, and there you can see we pass the object itself through in the payload. So in the Shopify code base, we have a subscriber that is built just to handle these protobuf events. When it receives an event, it's able to serialize the proto object to binary for transport over the wire by calling toProto on it. So this is why we pass the whole object through in the payload so that subscribers are able to interact with the object. In our case, we wanted to be able to call toProto so that we could serialize the object properly. We also register the subscriber with a filter to make sure the subscriber is only listening for protobuf events, since not all of our events are proto objects. And we do so pretty simply just by checking if the object responds to toProto. So ultimately, the event reporter doesn't need to know anything about protobuf or about schemas. All of this is handled in our subscriber. rails.event.notify is flexible. It lets developers pass in a hash or an event object. This means that we can use the same API whether we're creating a structured log or whether we're creating a business event with a schema. Under the hood, Rails becomes a little bit more complex. It has multiple branches for how the API can be used. But this is complexity that Rails gladly takes on because it gives developers a clean, easy-to-use API. So lesson number 3 is, when building for open source, always optimize for ease of use from the developer's perspective. Okay, the last part of the event reporter that we're going to talk about is the context store. So the context store stores information that applies to the entire scope of a request or job. This is context that we want every structured event within a unit of work to inherit. So this might include things like identity information, maybe a user ID or API client ID. It might include request or job metadata, or maybe even GraphQL query information like the operation name or the schema. Shopify's observability team built a shared context class to capture request-level metadata for observe.log. So basically how this worked is you could call shared context.declare with a set of fields, and this would create a new typed context store. So let's look at an example. We had a work unit context class, and this was used to hold metadata specific to the unit of work. So this was things like the shop ID. Most requests at Shopify are centered on a shop. It includes things like the pod ID, which is kind of like a shard ID for us, the request ID, and kind of other information that should be scoped to the request or job. So declaring a shared context generates a subclass with setter methods for each field. So you could call workunitcontext.shopID or workunitcontext.requestID to set those values for the duration of the request. The attributes could be read through this attributes method. So this is what we would use to then merge those attributes into every log created with observe.log. And then we would handle kind of clearing all of that context at the end of each request or job. So one key detail about Observe Shared Context was that it used Fiber local storage under the hood to hold the context hash. Fiber local storage was introduced in Ruby 3.2 for managing state within a specific scope of execution. With Fiber local storage, state is inherited by child fibers and threads, but changes in the child don't affect the parent. This makes it a really good fit for storing request-scoped data like this. Why is that? Well, let's look at an example. So consider this scenario. We have a request that starts, and we set some work unit context attributes, like the shop ID and the request ID, in the main request thread. Then a child fiber is spawned, maybe using the async gem, to run a database query. And inside that child fiber, suppose we emit a log using observe.log. We would want that log to include the context that was set by the main thread, but any further changes to the context within the child shouldn't affect the main thread. Fiber local storage actually just gives us this behavior by default, which is kind of cool. If we take a look at how shared context works again, you'll also notice that we actually duplicate the context hash and freeze it every time we write to it. And this is because the child and parent fiber, even though they have their own isolated storage, would both point to the same underlying hash object. So we use this copy on write approach by duplicating the hash anytime the context store is written to. Changes to the shared context stay isolated between fibers because we take a new snapshot of the context anytime we write to it. So our monolith had a shared context mechanism to track context for observe.log. We wanted the event reporter to support something similar out of the box. One option we considered was this class called active support execution context, which is a key value store that tracks request and job metadata throughout a Rails execution cycle. Execution context is private, it's not documented, but it is what powers, for example, the current attributes feature in Rails. The problem was that execution context wasn't using fiber local storage to store state. And that behavior that we just talked about was really important to us. We really wanted that behavior. Execution context actually uses another module, isolated execution state, it's a little confusing, I know, to store its data. Isolated execution state can be configured to scope isolation to either fibers or threads using a Rails config called isolation level. Both of these classes are singletons, which means setting the config controls how virtually all of Rails' internal state is isolated. Because of this, it is usually set based on your web server. If you're using a thread-based server like Puma, you would set isolation level to thread. That's the default. If you're using a fiber-based server like Falcon, you could set it to fiber. So at Shopify, we use Puma locally in development, and we use something called Pitchfork in production. Pitchfork is based off of Unicorn. It's process-based, so thread-based concurrency kind of works as an isolation level. So our isolation level was going to need to stay thread-based in order for our web server to continue working. But we wanted a way to use fiber local storage specifically for the event reporter. Tenderlove, Aaron Patterson, and I discussed possible options and decided to refactor execution context and isolated execution state so they were no longer singletons. We thought if we could allow independent execution context to exist, we could configure the main one that controls all of Rails' internal state separately from basically an execution context for the event reporter. So we opened a PR, which, spoiler alert, did not get merged. It's linked in the slide here if you're interested in having a look. Basically, we got pushback from other Rails core members. The classes we were trying to change were too tied to the framework's concurrency model to change safely, and the abstraction wasn't really clear enough. They suggested we build what we needed directly on the event reporter and then figure out how or if we wanted to align it with the execution context class later on. So lesson 4, avoid abstracting too early. When thinking about how to store request context for the event reporter, we jumped straight to trying to make execution context work for our use case. But we hadn't even upstreamed the event reporter yet, so our use case was hard to justify. Other members of the Rails core team pointed us in the right direction. Build what we need for the event reporter first, using Fiber local storage, and then see if execution context can be refactored later on. So we ended up building a set context method on the event reporter to replicate what observe shared context did. It actually looks very similar to the code we looked at with shared context. It uses Fiber local storage under the hood. It applies that same copy on write approach we saw earlier. Any context set during the request or job is then included in this context hash that comes with the event. And Rails handles resetting the context around a request or job automatically. Okay, to close, we're going to talk about upstreaming the event reporter. By November of 2024, we had a PR to introduce rails.event internally in our monolith. This is an approach we use a lot at Shopify. Before proposing an API to Rails, we first adopt it in our own code base to make sure we've built the right thing. At this point, we were pretty confident that the event reporter API met all of our requirements. It supported individual log entries with both hash-based payloads and events with explicit schemas. It was easy to integrate with Observe, but we'd kept Shopify-specific details out of the API. We provided consistent event shapes. We included request-level context tracking. And because we'd built it as a separate API, we knew the feature wouldn't clash with the Rails logger, and we expected that it would be easy to integrate with Rails framework notifications down the road. Once the event reporter was added, we started replacing all observe.log and rails.logger calls in the Shopify codebase with rails.event.notify. We ended up migrating over 11,000 call sites to the event reporter and removed all of our unstructured logs. This was right around the time that LLMs were becoming a thing, so LLMs made a huge difference in us being able to do this migration, and I imagine it would be even easier today with how much they've advanced. So by the summer of 2025, we were ready to propose a PR to add structured event reporting to Rails. The PR got a ton of community engagement and feedback, which was really great, and it was merged in August. Since then, there have been a number of PRs that have helped make structured events better. Bayrou Jean Boussier opened a PR to fix some loading issues and to better integrate the event reporter with the Rails error reporter. Zach worked on filtering sensitive data from event payloads, similar to how log filtering already works. He's also been working on a structured events guide for Rails. My colleague Gannon shipped a couple of PRs to emit all Rails framework notifications as structured events. This was that last requirement we talked about on the Rails side of integrating with Rails framework logs out of the box. And then outside of Rails, we've been seeing libraries like Honeybadger start shipping their own subscriber implementations to work with structured events. So the fifth and final lesson is that we build Rails together as a community. We developed the event reporter at Shopify based on our own needs, and then shipped a battle-tested version to Rails. But people outside of Shopify have worked to make the event reporter even better, and every one of you should feel empowered to contribute to Rails. Whether it's fixing a bug or proposing a new feature based on a proven solution in your own app, Rails depends on this community to keep moving forward. Contributing to open source doesn't have to be scary. If you'd have told me 10 years ago when I started writing Ruby that I'd be on stage talking about how to build open source, I would not have believed you. But I learned how to do it, and so can all of you. Remember some of the lessons we talked about today. Find the API that feels like Rails. Set strong conventions with what you build. When necessary, offer users a way to customize things in their apps. Design simple APIs that keep developers happy. Don't fall into the trap of abstracting too early. Wait for the pattern to emerge. And most importantly, take pride in being a member of the Rails community. Rails exists because of the power of open source. It's up to all of us to continue shaping Rails into the framework we need it to be. Thank you so much for wrapping up day one with me. It's been awesome to speak with you all today. I hope you enjoy the rest of the conference.